Okay, dear colleagues, welcome to BIMSA Integrable Systems seminar. There are so many people in the audience. So today's speaker is Sergei Oblezin from BIMSA, and he will tell us about Gelfand, Kapranov and Zelevisnky structures and representation theory.
Thank you very much for inviting Ivan and for this nice opportunity to give talk at BIMSA seminar on integrable systems. So sorry that the title of the talk in slides is different from the announced title, which I mean the original title is the title of the paper. Our paper joined with A.Gerasimov and D.Lebedev, published last year in the journal and like 2 years ago appeared in archive, and more earlier version with announcement of the main construction. So this work is a part of a larger project on study of relations between Langlands program and mirror symmetry, and or mirror symmetry of the underlying homogeneous and symmetric spaces. So in today's talk, I will let me start with the motivation, with the simplest case. So it is devoted to the Gelfand, Kapranov, Zelevisnky generalized hypergeometric functions. And let me start the original motivation. So I believe that many mathematicians know the Gauss hypergeometric function, which is, you can see above, defined as a series which is convergent when absolute value of the argument z is inside the unit disk less than 1. And so the series has 3 parameters, A, B, C, that are complex numbers and such that parameter C is not negative integer. Here is the standard definition of Pochhammer symbol to describe the coefficients, and this series is a solution of the hypergeometric equation, which you can find below, see below, and again there is also non-integral representation of the Gauss hypergeometric function given by this integral. Again, convergent for certain conditions on the real parts of parameters B and C. And this is a standard function. It is well known that many special functions in one variable z can be obtained by specialization of this function, hypergeometric function. And actually, yeah, so many orthogonal polynomial special functions arise from this function. And I would like now to explain how this function fits into the group theory setting. Mainly, it was an old project, probably started in 50s or in 1950s, and the idea was to set all the well, as many as possible special functions into the group theory setting, and to of course this idea has lots of applications, and in particular, I think it was known for probably many years, probably century before that or more, that special functions allow lots of symmetries and identities which are source of very interesting and influential insights and hints to many areas, other areas. And that's why there was, of course, already for a long time before 50s and 60s, idea how to, so there should be some group theory symmetries behind the symmetries of special functions. So since hypergeometric function is supposed to be one of general functions in one variable, generalizing or like unifying many special functions in one variable. So it was a like first exercise to first step is to put it into a group theory setting. So the underlying group is the group of unimodular real matrices SL to R. So it is just 2 by 2 matrices with determinant 1. Then there is a subgroup of rotations. And there is another so-called Borel subgroup B. I here choose lower triangular matrices. So then there is Iwasawa decomposition or Gram-Schmidt orthogonalization procedure shows that arbitrary unimodular matrix can be decomposed into in unique way into product of one matrix, lower triangular matrix, and the rotation matrix. And so this can be done explicitly. So the explicit formulas are below. And also here, I would like to remind also Gauss decomposition of any 2 by 2 matrix as a product of lower triangular and upper triangular matrix. So there are just depending on whether in our 2 by 2 matrix alpha, beta, gamma, delta, whether alpha is 0 or not 0, there are 2 ways to do it. So you see the appropriate decompositions in the last line of the slide. And this is just standard facts about the group of unimodular matrices. So now representation theory. So we consider the induced representation from the subgroup of lower triangular matrices B. So we choose a character high. Character has 2 parameters, is determined by 2 parameters mu and epsilon, where mu is arbitrary complex number and epsilon is either 1 or 0. And the corresponding representation, induced representation space, it is just consists of functions, equivariant functions, B equivariant, on the group of matrices. So it is arbitrary function in our 2 by 2 matrix such that if we multiply from the left by any lower triangular matrix, so we have this character multiplier and function. So the group acts in the standard by standard left action. So we multiply argument of any function from the right. And in our representation, there is a pairing, just standard L2 pairing, which is integral over upper triangular unipotent matrix. So this is yes. So in particular, when we specify parameter representation parameter mu in this way, so it is lambda is real. So when it is mu is of the form I lambda minus 1, then operators of representations are unitary with respect to this pairing. And this is just again standard facts about induced representations of the group SL to R. So I just would like to emphasize this is induced representation, so-called principal series representations of the group. So they don't contain highest weight vector. So they are just so this is infinite dimensional representation called principal series. So induced from the subgroup of lower triangular matrices. So yes. So now in we would like our main construction will be that we will identify the hypergeometric function with what is called matrix element in this Prince series representation. So once we have infinite dimensional space and pairing, so between F1 and F2 here. So F1, F2, we apply the same reasoning as if they are vectors in this infinite dimensional vector space. So matrix element, we substitute some functions F1, F2, apply L to pairing and obtain the hypergeometric function. That's our strategy, and that's the construction, classical construction from 60s of, I think 50s, 1950s. So we define the following vector called generalized spherical vector, phi mu. And this is spherical because it is actually it is a character of the subgroup of rotations. So that's why it's called spherical vector. So it is like semi-invariant under the action of the rotation subgroup. So, and here it is a character of this subgroup K. Then general, again, statement, classical statement that the Jacobi function, it is called Jacobi function, is the matrix element of the two vectors, phi nu1, phi nu2, nu1, nu2, two different characters, well, in general, different characters of the rotation subgroup. And here we put, so it is a function in, so it is a matrix element function on the diagonal matrices. So here E of X is argument of the diagonal matrix, and we just insert, so in the right, on the right vector phi nu2, we act with this diagonal element of our group. In this way, please note that this matrix element is dependent on three parameters, mu1, mu2, and mu. And epsilon 0 or 1, but here epsilon measures, epsilon measures because nu is chosen to be even. That's why adding or not adding epsilon covers all cases of integer nu. So this function has three parameters and can be identified with the Gauss hypergeometric function via substitution z, which is argument of the hypergeometric function, is the inverse square of hyperbolic sine x. And the relations between the parameters of the matrix element and the parameters hypergeometric ABC are subjected to these relations. So this is again classical construction, and please note there is of course if you remember, general hypergeometric function Gauss ABC are arbitrary complex numbers, and here of course mu1 and mu2 are integers, and mu is arbitrary complex. So it is not any hypergeometric function with arbitrary A, B, C can be obtained in this way, but again with 3 independent parameters, but restriction that some of parameters are like integers. So after this was realized, and this is presented in many books, in several books. So this is a classical result. Then there was posed an absolutely natural question: how to extend and generalize this or other construction to multivariable case. So there was several groups or even generations of mathematicians. So I mentioned only probably 3 who initiated, like Gelfand, Kornwinder, MacDonald, but there were many more working in this direction on general hypergeometric series. It was, I mean, people were working, of course, started working on it much before that. But here I put it assuming that it is in the representation theory setting. So how to generalize the hypergeometric Gauss hypergeometric function to stay general enough to several variables z, and keeping again Lie group symmetry, so that it is some either spherical function matrix element, so something that has a standard description in terms of group theory. So this is again I would say the classical question, and then since it is integrable system seminar, I would like to comment on how hypergeometric function of this Jacobi function can be identified with a wave function of an integrable system. So yeah. So it is the corresponding integrable system is Calogero-Sutherland system corresponding to the root system BC1. So the construction is here I follow the against quite standard construction of representation theory description of quantum integrable systems from 70s. So again, there are many names, and Alshanetsky, Переломов, Kostant, Kazhdan, and many other people. So in our principal series representation, we define the infinitesimal action of the Lie algebra of our group, which is defined like this. So it is infinitesimal left action. So we multiply argument of our function by exponent this one parameter subgroup of the corresponding Lie algebra element, and then differentiate over t and take limit t to 0. So standard construction of infinitesimal action of the Lie algebra. And it is easy to see that in this principal series representation, if we choose this standard basis of SL2, so the action will be of the generators of Lie algebra will be like this. So then in the center of the universal enveloping algebra, we have Casimir element C2, which is by definition, Casimir elements are those elements, so they are like polynomials in our generators EFH, such that this polynomial commutes with all elements of Lie algebra, in particular with each generator. So then substituting into this Casimir element the generators, you can see that the Casimir element acts in this representation by multiplication by scalar, which you can see as another implication that this is an irreducible representation. And so by Schur lemma, this central element which commutes with all generators of Lie algebra acts by scalar. Then following this scheme, again, standard scheme, we define the action of this Casimir element in our representation defines is equivalent to the action of certain differential operator when we insert it in the matrix element. So we know that on the one hand side, since the Casimir element acts by scalar, on the other hand, by substituting acting on left and right vector in matrix element, it acts by differential operator. So this gives rise to the eigenvalue problem for this differential operator, which is, as it is announced, Calogero-Sutherland quadratic Hamiltonian and of type BC1. So there are these two. So here root system, you see there is a short root, which is sine x and sine 2x. So it is BC1 with arbitrary coupling constants. And of course, you can get rid of first derivative by a normalization of this matrix element. So multiplying by, I think it is hyperbolic sign. So you can get rid of this. And this gives identification of the normalized matrix element with a wave function of the Calogero-Sutherland system. So as we have mentioned, so for the Gauss hypergeometric function, we have a representation theory description. So it is a matrix element in some infinite dimensional representation. On the other hand, it is a wave function of some quantum integrable systems. And if we are thinking about generalizing the hypergeometric function to multi-variable case, we should have this in mind. And when we look at some candidates to the appropriate generalization, we should have in mind its representation theory description and relation with quantum integrable systems. Any questions so far? So now just to the solution, there are actually several solutions of generalized hypergeometry. So the Gelfand, Kapranov, Zelevisnky is one version, which is known to naturally related to toric geometry and mirror symmetry. That's why we are interested in this one. So it is due to observation by Gelfand in 80s, probably earlier, but it is in paper in 1980s. So if we consider the normalized hypergeometric series like this F tilde, then it has been known again from the times already by Gauss that the hypergeometric function satisfies certain differential difference equations. And here they are. So after suitable normalization, so you can write it in this simple form. So here it is derivative over z. Here you see all. So this is differential difference equation and three difference equations. But you see here the right-hand side is the same as here, so you can substitute into the right-hand side of these three equations the derivative. So this is a system of differential difference equations. And this system, they are known as Gauss relations. And mainly you can derive from this system of equation the original hypergeometric second-order differential equation. So this is just a, but the observation that the appropriate generalization of proposed by Gelfand, Kapranov, and Zelevisnky is in this form, it should be generalized. So we replace the original second-order differential equation by a system of very simple first-order differential difference equation. So we see here it is first derivative, and here just shift by one. And in this form, you can generalize. So this is the answer. So this is the GKZ GG data, which GKZ is Gelfand, Kapranov, Zelevisnky, and GG is Gelfand, Graev. So GKZ appeared first at the end of 80s, like 1987, 1988. And then later, after several years, the Gelfand with Graev, they found more nice form, equivalent form, how to rewrite the GKZ system, and it is GG hypergeometric. And so this is the so this GG function, Gelfand-Graev function, associated to the same combinatorial data, but just different solutions. So let me introduce it. First, this A, it is a collection of n. So I is just a index set of n element, capital N. So we have n vectors in the lattice Zm of full rank. This means that this collection of vectors generates Zm as a free abelian group. So in particular, n should be greater or equal than m. Then we introduce this called relation lattice. It is like dual object. It consists of vectors, integer vectors, such that all such vectors L, such that such linear combinations for these A's is 0. So then we choose a basis here in this relation lattice by L alpha, and the rank of this relation lattice is index set G. So it is n minus m. So these two numerical invariants of the GKZ data, n and small m. So here it is n minus n. And the relation matrix condition, this can be rewritten in matrix form. So if we write down, collect these vectors into a matrix, rectangular matrix, and here we take the matrix again consisting of these generators L alpha, then the relation lattice property will be just this orthogonality relation. So just A times M transpose matrix is the 0 rectangular matrix. So this is the combinatorial data. Using this data, you can define a toric variety. And so, but I won't go there in this talk, and we'll just focus on representation theory part. So now the Gelfand-Graev system. So having this data of collection of vectors A and these two index sets M, N, and J, we are looking for a function. So GG, hypergeometric function, is a function in n variables U that are in this cone. So positive part of R to the power n, and complex like spectral parameters, so complex parameters gamma, n of them. And this is system of equations. So here, for every vector L in our relation matrix, this equation holds. Here you see product over all L that are negative, here equals to product of all L positive. Now, this is difference equation. So this is differential equation, difference equation. This is again differential equations, and this is again difference equation. So Gelfand and Graev proved that this system is holonomic, which means it has finite dimensional space of solutions. And you see why they put. I won't put you the definition here. I won't show you GKZ system, but I just want to emphasize that in this form, it is more convenient to look on this system from the perspective of integrable systems, because as many wave functions for integrable systems, like you have here n spectral parameters, n time variables, and you have integrable system and dual. So pair of differential equations on continuous variables U and on real variables U, and difference equation on this complex parameter gamma. So it is a symmetric form. And this is called the Gelfand-Graev system. So the original definition by Gelfand, Kapranov, Zelevisnky, it is not symmetric. It is a differential system and of several equations and one difference one. So this is the symmetric one. Any questions? Comments?
Only in the end, or some?
No. It's much more general. Yeah, it's much more general, but it should contain. Yeah, I will comment on it. Yeah. So yes, that's one point, that there is one direction is to consider generalization of hypergeometry related to BCN root systems. This is different direction, and which is, I believe, more general, but to my best knowledge, it is not shown. And I think should be checked. So here, to demonstrate the broadness of this definition, let me show you simplest examples of Gelfand-Graev function. So in one simple case, when parameter n and m equal 1, we just take one parameter, then the set J, which is of size n minus m, is empty set. Then the above system of 4 equations, so 2 out of 4 equations degenerate, so they make no sense. We get one difference equation, and the solution is the gamma function. The other simplest case, when we take n equals n minus m and equals 1, and parameter m is 0, then the other pair out of 4 equations degenerate, and here it appears one difference and one differential equation, but I mean the other ones out of 4, and the solution is this function, which, as you may notice, integrand of the gamma function. So you see that the same system, GG system, it is first advantage, it is symmetric. Second, it is like covering things like see-some duality. So you see the gamma functions and its integrals. Yeah. Any other comments, questions? So now, another example how to derive, obtain our original Gauss hypergeometric function in one variable out of this data. So we consider the set of these vectors, 4 vectors in 3D lattice, integral lattice, and take this relation lattice generated just by one vector. Then the GG system, by definition, takes this form. So it is 1, 2, 3, 4 equations in 4 variables. So we have U1, U2, U3, U4. Then substituting 2 and second and 3, 4 into the first equation, which is of second order, just after very simple manipulations, you get this identification. So a generalized hypergeometric function equals f of z, and where u1 is z and u2, u3, u4 are 1, specified 1. So please note here that the Gelfand system is very general. So to describe effectively describe the hypergeometric function classical in one variable, we introduce 3 extra variables. But the price that we pay, the equations are very simple and have very transparent and clear combinatorial description, which allows for generalization. So this is what's going on. And this is the idea. So now I want to just show choose one solution to the Gelfand system. And because, as I mentioned, it is holonomic, there is a finite dimensional space of solutions. So we are interested in these special solutions of this form, and I comment later why this is interesting. So again, here size parameters sets I, J, R, and M. And then this integral is a solution of the Gelfand system. So please note that here I put the full code, but here is a product of delta functions, which means that they constrain the integration domain C, which is defined by this relation lattice L. So here we have these components of these basis vectors L alpha, spanning the relation lattice. So this means that here you can see the integrand function is absolutely standard as for just gamma function, but integration domain is defined most about the GKZ data. So here it's only about the size, so number of variables that we take, and gamma spectral parameters. So the integration domain actually knows the data. And the main result of our paper, of the talk, is answering the question how to identify this function, this solution of Gelfand system with certain matrix L of a group-like object. And the second result is how to obtain Gelfand system in terms of some Casimir element of some, yes, Casimir. this Lie algebra of this group-like object. So this is in the remaining time. I just give these two answers. Any questions? So now what's the group-like object? Mainly, so for having index set, we define this Lie algebra Ln with a generator CFH and central element. Here are commutation relations, but the idea that EI, FI, and C, it is Heisenberg algebra, and H are Cartan generators. So it is a so-called oscillator algebra, dimension 2n+1. So we have Heisenberg algebra and adding the Cartan subalgebra commutative. Yes, so this is the Heisenberg. So this is just a, I mean, very simple object, and again, the transparent, clear physical meaning, and also, of course, meaning in the sense of integrable system set. Yes, and that's it. Now representation. So we choose for these parameters that we have in the GKZ data. So we have a complex gamma. We consider the representation of this oscillator algebra in the Schwarz space. So the generator E x by first derivatives, F multiplication by T, Cartan generators, quite standard Cartan generators, and the C center x by 1. So then there is a pairing. We consider dual module. And here is the just pairing like L2 pairing, but on the cone. And we define action of the in the contragradient representation using this condition of the pairing, so that it is just contragradient operators as adjoints as usual. And this is expression for the action of the oscillator Lie algebra in the contragradient representation. So, here the essential point that generators F are invertible, and this is plays important role in our calculations, so that we formally can localize the universal envelope in algebra and consider F invertible. So this is the representation data. Yeah, so representation is Schwarz space, then dual representation is distributions of generalized functions, and so that's how delta functions appear. So now we define our vectors in the matrix element. So vector, one vector here, it is right. It is eigenvector of the generators E. So it is, if you know, like a coherent state. And the covector here, phi, it is defined using combinatorial data of the GKZ system. Please note again, here phi knows nothing about the GKZ data except the number of variables, and covector knows about the relation lattice and matrix A, our vectors, which will which affects that the covector contains the delta factors that describe the integration contour. Then proposition saying that the solution of to the Gelfand-Graev system, Gelfand-Graev function, can be identified with this matrix element. So with the two vectors, find this calligraphic phi, again with the action of Cartan elements. And the proof is absolutely straightforward. So it is just using a representation, we solve the differential equations, just find vectors, substitute it in the matrix, and then obtain the integral. So it is like 2 lines. Proof is simple. So now let's comment on the equation, how to obtain the Gelfand equations from this oscillator Lie algebra. So I recall the definition. If we have a module of the universal enveloping algebra with parameter gamma, then the primitive annihilation ideal of this module is the those elements in the universal enveloping algebra such that if you substitute into this polynomial the representation generator, they will vanish. So this it is standard again construction like Dixmier that it is ideal in the universal enveloping algebra. And then for any vector in our integral lattice, we consider this element in the universal enveloping algebra. So there is a simple lemma, well, technical lemma, checking using actually commuting derivatives and multiplication by t. It vanishes, so it belongs to the ideal. And then proposition that now if we assume that those s are vectors in the relation lattice of the Gelfand system, then this identity implies the Gelfand equation. So mainly we again insert this element X into the matrix element and just calculate the corresponding differential operator and obtain exactly the Gelfand equation. And here in this proof, it is essential, as I said, that operator F is vertible. So here we localize the universal enveloping algebra and just and yeah, so here so mainly we can divide by products of the F to proving this. Any other questions? So now I want to now come to a bit to give you hints and comments to like mirror symmetry of flag variety. This is about the Whittaker functions. So Whittaker functions are some special functions on a group. Here is the definition. Again, for SL2, it is a of course degeneration of the Gauss hypergeometric function. It's specializing the parameters ABC and taking certain limit. And in general case, Whittaker functions are defined in group theory setting. So the definition was proposed by Jacquet in his thesis, and I will use the form of constant proposed in 70s, constant construction of Whittaker functions. And yeah, so the why Whittaker functions? Because Whittaker functions are generating functions of quantum cohomology of full flag varieties. That's why they naturally come in the homological mirror symmetry. So again, it is just a hint. So now we consider take lambda, again, complex parameter. We consider principal series representation of GL L+1 of the general linear Lie algebra. Again, dual contragradient module and the pairing. So now we define here the triangular decomposition our Lie algebra GL. So and minus nilpotent, lower nilpotent subalgebra, Cartan subalgebra, and positive nilpotent subalgebra with the choice of roots. And here we define the so-called Whittaker vectors in our representation W. So the right Whittaker vector, it is eigenvector with respect to generators of n plus. Left Whittaker vector, eigenvector with respect to, well, it is covector in the contragradient representation under the action of n minus. And then the Whittaker function is defined to be this matrix element. Here covector, vector, and here again general Cartan element of the group, I mean exponential. So here we impose that the action of Cartan subalgebra in GL L+1 integrates to the action of the Cartan, the appropriate maximal torus in the group. Yes, so now the GL Whittaker function affords such remarkable integral representation. So this integral representation, I will comment. So originally it is related to the integral proposed by Gelfand, proved mirror theorem, and but Gelfand introduced his integral with this lambda 0. So then later it was other people entering lambdas, and we in our paper in 2007 we described it again as a matrix element and constructed the appropriate representation of explicit realization of representation of universal envelope in algebra by differential operators and obtained this formula. So again, when we put lambda to 0, we reproduce this integral takes this form, which is called stationary phase integral by Gelfand. And here in the exponential, we have some of other exponentials that can be encoded in by arrows in the Gelfand-Zeitlin graph. So mainly you have this graph with arrows here, x1, x2, xl+1. They are it is just argument of the resulting function and integration over this triangle array of t's. So in this form, it is natural to expect that this function, Whittaker function, can be described in the setting of Gelfand-Graev system. And so this what we do. So mainly this is just the corresponding combinatorial data. So we denote D is the dimension of the nilpotent subalgebra or unipotent subgroup. So we take the set E is the set of arrows in this graph. D is the set of vertices in this graph. So we have arrow and vertices. Introduce integration variables that are just arrows. Then these are arguments in the resulting function. So we introduce extra variables because here, as you can see, for example, you see here A and B. So B only B K enter with non-zero exponents. So B, K, J, K not equal J, they just have power 0. So this is definitely, it is clear from here, for example, that it is a reduced GG function. So this is the general Gelfand-Graev function, and which can be reduced to the Whittaker function by some constraints on these spectral parameters gamma nu and on the these variables y and z, reducing them to the maximal torus, so to obtain this x. So this again first has several implications, and I just the concluding remarks is that on the one hand side, I should mention connection with integrable systems is that here Whittaker functions are wave function to quantum Toda lattice, quantum Toda integrable system. And of course, you may notice that if you look at Gelfand graph system as a certain integrable system associated with this oscillator Lie algebra, so this is gives some degeneration, and in particular, you get for the Whittaker function two different matrix element representations. So one related to the general linear Lie algebra, and the other to the oscillator. So mainly there is this like symmetry between oscillator Lie algebra and general linear Lie algebra provided by, of course, this special choice of coordinates and by this very special integral representation. So here, because we choose the solution to the chain Whittaker function, very special integral representation, and then we are able to identify it with a solution of Gelfand graph system. So if you take, there are other integral representations for Whittaker function. If you take another one, there is no any evidence that it can be done. So this is provided by very special choice of this actually Gelfand integral representation, which is not surprising because Gelfand used it to prove the mirror theorem and used the toric degeneration of like varieties. That's why, of course, the GG system is also, it is a combinatorial data for toric varieties. It's natural to identify it this way. And so that's, let me probably stop here. I would like to finish here. So thank you very much. And please ask questions if any.
Hi, so can I ask several questions? Hello?
Yes, hello?
Yeah, so your wave function like on this page is defined on Gelfand and Zelevisnky graph.
Yes.
So why we I mean, I understand that we're integrating on some Lagrangian manifold, but why it's Gelfand and Zelevisnky?
Why it is Gelfand-Zelevisnky?
Yeah. So is there an intuition that I should expect this?
Well, yes. So thank you for this question. So this graph appeared in the original paper by Gelfand, and of course there was no. It was not called as Gelfand-Zelevisnky graph, but later when we proved Gelfand's formula in the representation theory setting and constructed the appropriate realization of infinite dimensional representation by differential operators, then it became more clear that it can be identified with the Gelfand-Zelevisnky graph. So which is, I mean, like with Gelfand-Zelevisnky patterns for finite dimensional representation. And this can be seen explicitly if you want to see this can be done by if you take the Gelfand-Zelevisnky formula for Q Whittaker function, or Q deformed Whittaker function obtained in our other paper, and then take limit Q to 1, then you will solve the Gelfand settling formula for Q-deformed Whittaker function will reproduce this formula, and the Gelfand settling patterns for the Q-Whittaker function will degenerate to this graph.
Okay, so I mean, Gelfand definitely appears both nice, but it also has cause of problems. For example, like in type BCD, every time your dimension would jump by 2, so we don't have nice Gelfand definite pattern there. So how could we generalize this to other Lie algebras?
To other Lie algebras.
Right.
Well, this of course can be done for classical Lie algebras, because in our paper in 2007 we constructed these integral representations for symplectic and orthogonal Lie algebras, and they also reproduce the appropriate Gelfand settling graphs. And yes, it is a very good exercise to obtain those integral formulas from the relevant Gelfand graph system. Of course, this is doable because there it is also toric degeneration and there is toric variety. So this is, I think, yes, a good topic for me.
Okay, so the other question is like at first, this hypergeometric series is it actually comes from this Kajira-Moser, and it's more or less related with the spherical representation.
Yes.
And the Whittaker actually is related with the Whittaker model of this SLN, for example. So what I'm wondering, like, what's the duality, the symmetry, like mirror symmetry that you are referring to?
So this is I think well, for me it is two different questions. So one question was about spherical vector and Whittaker vector.
Right.
Yeah. So this is so when you construct, yes. So when you take two Whittaker vectors in the matrix element, you get the this is constant construction of Whittaker function, and you get generating function quantum cosmology of flag variety.
Right.
But in the setting of, as I explained, yes, in the beginning for the hypergeometric function, I took here two spherical vectors.
Right.
Here, instead of psi, I put phi and phi. So in fact, yeah, so that's why it is different. And for so for hyper, it is, I mean, it is different. It is different mirror symmetry. So here it is for the mirror symmetry on flag manifolds, you take this one. So the Gauss hypergeometric function, I think you consider it is just different. It's not flag variety. It is some other space that you study. Yeah.
Okay. Okay. You mean actually the hypergeometric one, that their mirror symmetry comes from this toric varieties. Maybe.
Yes. Well, of course, if you consider in the toric setting, there will be appropriate toric varieties. So question like what variety you degenerate to obtain this toric variety. Yes.
Okay, but this Gelfand gravity hypergeometric function is defined through this Heisenberg subalgebra,
yeah,
like Ln, and
yes.
So how do I I mean how do I get it from a classical Lie algebra?
So again, from classical Lie algebra.
Yeah, it seems it doesn't depend on the Lie type, or I'm understanding it wrongly.
This is absolutely correct. So actually, what's going on? You start with classical Lie algebra, say. So you have its flag manifold, Then you have quantum cohomology and you have Whittaker function as a generating function. But then for mirror symmetry, you take this plug manifold and you degenerate it to obtain a toric variety. And this toric variety has symmetry, this oscillator algebra.
Okay.
So this oscillator algebra knows only the combinatorial data of this toric variety.
Okay.
That's a good question. If you can reconstruct from here root data of the original flag variety, that's a good question. Yeah. But,
okay. Thank you. Thank you. Thank you. So you're telling me actually like their functions from their functions I'm degenerating from hypergeometric to confluent hypergeometric, but for their varieties actually I'm degenerating in an opposite way direction, because I'm degenerating from a flag variety to this toric variety.
Yes. What do you mean?
I mean this hypergeometric one is constructed from this oscillator layout.
Well, yes. So you can think of this oscillator algebra as a degeneration of GLN. I mean, this is reductive. Yeah, this is non-reductive free algebra. So you, so instead of EF, you get Heisenberg. So obviously you degenerated some reductive free algebra and obtained this non-reductive.
Right, but their functions is actually degenerating from the other direction, because I can only degenerate from a hypergeometric function to confluent one, which is Whittaker.
Could you repeat again?
I mean, you're just saying that from their algebra side or from the variety side, I'm degenerating from a flag variety to the toric variety.
Yes.
Or I'm degenerating from SLN to this LN, but their wave function, I mean their wave function associated with LN is a hypergeometric function, and the wave function associated with SLN is actually a Whittaker function, which is a confluent hypergeometric function.
So yeah, as I see what you mean. Yes. So this is true. I mean, this is what happening, but please, so mainly I probably repeat the question. So so we obtain this integral representation for Whittaker function from degeneration of this Gelfand function. And you say like Whittaker function corresponds to flag variety, and this corresponds to some toric variety. But please note that this toric variety that we take here, it has much larger dimension than the original flag variety.
Okay.
So you obtain toric degeneration of flag variety on the one hand side. On the other, you take larger toric variety and specifying you obtain that toric degeneration.
Okay.
Like that.
Okay, thank you. Yeah, I think I finished my question. Yeah. Thank you.
Thank you very much for the interesting question.
Any more questions? Yeah, if not, but thanks, Sergei, again.
Thank you very much.